Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to do a sample problem of nuclear reaction rates. In the last video, I kind of explained everything, but I wanted to give one more problem to help students that might need to see this one extra time. So when we're dealing with nuclear reaction rates, we have two equations that we work with because nuclear reaction rates are first order kinetics, and both of these deal with first order kinetics reaction rates. Okay, so the T1 half is your half-life time, K is your rate constant, A sub T is the amount at time T, so it always matches this time. So if this is 2 hours, then this is the amount at 2 hours. Okay, and A sub 0 is the amount at time equals 0, or what we call the initial amount. Okay, so what I'm going to do first is I'm going to try to figure out what the rate constant is equal to, because we need to use the rate constant in the second equation. To figure out the rate constant, what K is, you need the half-life time. And in this problem, the given is telling us that the half-life time is 22 seconds. So let's figure out what the rate constant is first. So I'm going to take my T1 half is equal to 0.693 over K, and I'm going to rearrange it so that K is equal to 0.693 divided by the half-life time. And if the half-life time is 22 seconds, I just go ahead and plug in 22 seconds right here. And I take 0.693, divide it by 22, and I find out that the half-life is, that the rate constant is going to be equal to 0.0315. Now, seconds is in the denominator, so we call that seconds to the negative 1. And this is my rate constant. So that's the first thing that I need to solve. So then I'm going to take this equation, which is called the integrated rate law, and I'm going to write it down. The natural log of the amount at time t minus the natural log of the initial amount is equal to negative kt. Now I know what k is equal to. We know that this is going to be equal to 0.0315. Okay. We know that the time is 47 seconds. Okay. So we got 47 here, seconds, and this is seconds to the negative 1. So you can see that these units are going to cancel out eventually. And we're given the amount at time t as 3.81, and we're trying to solve for the initial amount. So this is what we're trying to figure out. So I have everything that I need except the unknown, which is going to be the amount at time equals 0, or what we call the initial amount. And let's go ahead and let's start solving this problem. Okay. So in my calculator, I'm going to take the natural log of 3.81, and that gives me the number of 1.34 minus the natural log of the initial amount. And I'm going to multiply these two together. So 0.0315 times 47, remember there's a negative there, is going to equal negative 1.48. And so right now, I'm going to subtract 1.34 on both sides. And that's going to make this negative even bigger. So I get negative natural log of the initial amount is equal to negative 2.82. I'm going to multiply both sides by negative 1, and that's going to get rid of my negative numbers. Okay, and this is where students typically get stuck, right here. Okay, so a natural log has the base of e. So in your graphing calculator, like if you have a TI-84, you're going to hit second, and then you're going to hit natural log, and you're going to get base e. And that's going to let's cancel out this side. And what you do to one side, you have to do to the other side. So it's going to be e to the 2.82. And if you plug that into your calculator, e to 2.82, you get an initial amount equal to 16.7. Okay, we'll call that 16.7 grams because that was the unit for the amount at time t. Now what I want to do is I want to double check that answer. Okay, I'm going to double check it with this chart. So we're going to always set it up as time equals 0. Okay, and we're saying that the initial amount is 16.7 grams. Okay, now what that means is that what it means from right now, I should say, is that for each half-life, it's going to get divided by 2 because that's how half-life works. Okay, so I'm going to grab my calculator here, okay, and I'm going to divide by 2 each time we have a half-life. So after the first half-life, how much time went by? Well, each half-life is 22 seconds. So after 22 seconds, this is going to be cut in half. And I already did it. I have it on my paper. It's 8.39 grams. After the second half-life, I have 44 seconds have gone by because 2 times 22 seconds is going to be 44 seconds. And this is going to get cut down in half again, which is 4.19. After 3 half-lives, so 3 half-lives, each half-life is worth 22 seconds, so we're at 66 seconds, okay? And if I cut 4.19 in half again, it's around 2.10, okay? So let's see if all this makes sense, okay? If this is my initial amount, if this is my answer, okay, then the stuff in my givens should fit. So at 47 seconds, where's 47 seconds? It's right here. It's just past the second half-life. They say that there's 3.81 grams. Well, is 3.81 just below 4.19 and above 2.10? It is. So that makes this answer make a lot of sense. So I think it's a viable answer to our situation here. I really encourage you to make these charts at the end, because I've seen students that tell me that the initial amount is some type of crazy number. Sometimes they tell me it's lower than 3.81, and that makes no sense because after 47 seconds, there's 3.81. So always double check your answers by setting up this chart. Make sure your answer makes sense, because there's a lot of places where the math can go wrong. If you found this information helpful, please give it a like and subscribe. And when you add a comment, it really pushes this algorithm to students that might be interested in learning chemistry.